Yeah, so this is joint work with my student Yingjie, and our work is about SDP relaxation for the Gaussian mixture models. So I assume everyone knows what the Gaussian mixture model is. We have several unknown cluster centers, and we have endpoints generated from a Gaussian distribution around these centers. But we can also consider more general sub-Gaussian mixture model. And our goal is to recover the labels of these points. We are interested in the clustering problem. We want to find out these underlying clusters of these endpoints. So the Gaussian mixture model, of course, has been studied for a long time. There are many, many different algorithms proposed and analyzed for this problem, but we are interested in a specific class of algorithms for this problem that is based on convex relaxation, or more specifically, semi-definite programming relaxation. So to write down the SDP relaxation for this problem, we will encode any candidate clustering by a so-called cluster matrix. So a clustering can be represented by a n by n CO1 block diagonal matrix that looks like this, where you have 1 between on entry ij if no I and no j are assigned to the same cluster and 0 otherwise. So with this as our variable, we can write down a very natural integer programming formulation for this problem. We try to minimize the total within cluster square distances, subject to the fact that our variable y has these cluster structures, such that it represents a valid clustering of the points. And this is an integer program, but we can write down its convex relaxation, SDP relaxation, by dropping this non-convex constraint and replace it with several convex constraints. Y is SDP, positive semi-definite. Its entries is between 0 and 1. All these are convex constraints. So we have a convex relaxation of the original integer program. So this SDP relaxation is not new. It has been studied before, and people know that in general, the optimal solution of the SDP relaxation is not integer and may not have the structure of a cluster matrix. And there are a long line of work that tries to develop clever rounding procedure for the SDP solution and try to prove bounds on the approximation ratios of this rounded solution. But in our work, we take a different perspective. Instead of analyzing the approximation ratio or doing this clever rounding, we will look at the original solution of the SDP relaxation without any rounding. And we will study its so-called estimation error, which is the distance of the SDP solution to the ground truth clusters represented as a matrix. And it turns out there is a very interesting phenomenon which we call hidden integrality, which says that although the solution of the SDP relaxation is not integer, its error, its estimation error, defined as above, can be bounded by the same error of the integer solution. So we have a convex relaxation of an integer solution, integer programming formulation of this problem, but it turns out the SDP solution inherits some of the properties of the integer programming solution, which we call the hidden integrality property of the SDP. So more specifically, we will consider actually a stronger version of the integer program. We assume that not only we have access to these points xi, but we also have an oracle that reveals the true cluster centers. And given this knowledge, and if we encode the clusters using a different representation, then we can write down another very natural integer programming formulation for this problem, where we simply minimize the distance of each point to its assigned center, subject to the constraint that your matrix has this clustering structure. So this is what we call an oracle integer program, because it also knows the true cluster centers. And with this integer program, we can prove the following main theorem. We can show that under some appropriate condition on the SNR, the signal-to-noise ratio, or the separation between the cluster centers, we can show that the error of the SDP solution, defined as the entry-wise L1 norm distance to the true cluster solution, is bounded by two times some appropriate version of the error of this Oracle integer program. So I'm not going to parse what this term means exactly, but the general idea is that on the right-hand side, I have the error of the convex relaxation solution. On the right-hand side, we have the error of the integer programming solution, and it turns out the SDP error is bounded by two times the integer program error. And so once we have this general theorem, then in order to bound the SDP error, it suffices to bound the integer program, the error of the integer program. And bounding the right-hand side turns out to be a much simpler problem because there are only finitely many feasible solutions to the integer program. And we can actually show that under the Gaussian mixture model, the error of the integer program is bounded by this expression that decays exponentially in the signal-to-noise ratio of your problem. And combining the previous two theorems, we immediately have this bound on the estimation error of the SDP relaxation. It shows that the SDP relaxation achieves an error bound that decays exponentially in the signal-to-noise ratio. And we can explore several consequences of this general error bound. By the way, so here we are bounding the error of this SDP solution, which may or may not be integer. But if you are interested in an explicit clustering, you can easily obtain one from this SDP solution. And it turns out the error of the clustering is also bounded by the error of this SDP solution, which is in turn bounded by this exponentially decaying term. So some consequences. First of all, our error decays exponentially in the signal-to-noise ratio, which is an improvement over a previous result, which shows that the error decays polynomially in the signal-to-noise ratio. And we also show that because the right-hand side decays very fast, exponentially in the signal-to-noise ratio, so if your SNR is sufficiently large, then the right-hand side is smaller than the numerical error, in which case the SDP solution is actually exact, in the sense that it equals to the true clustering exactly. And this happens when these two clusters are sufficiently separated. But our results is applicable even when these two clusters are overlapping with each other. In that case, we can show that although we cannot recover the cluster labels of all points, we can recover most of them. If the SNR satisfies certain conditions, we know that SDP can misclassify at most delta fraction of the points. And one interesting corollary of our results is in the so-called stochastic Bohr model. So the stochastic Bohr model is a special case of the Sub-Gaussian mixture model and a sibling of the Gaussian mixture model. So we assume that these points are not generated from a Gaussian, but instead generated from a Bohr uniformly from a Bohr around these clusters. And there are several previous results on this problem that show that if these Bohrs are disjoint and sufficiently far away, then you can recover the clusters exactly by solving the SDP. But our result is actually applicable in a more challenging setting. So even when these Bohrs overlap with each other, in which case exact recovery is not possible, we can still have a bound on its misclassification error. We can still recover most of the points, even when these Bohrs are overlap with each other. And actually, it's a little bit surprising that even if the distance between these two cluster centers is only 1/d distance away, which is much smaller than the radius of the Bohr, we can still recover the labels of most of the points. And I also want to mention that our very similar results apply to the so-called stochastic block model. So for that, for people who know this model, we can write down a very similar SDP relaxation, and we can have a very similar bound in terms of the SDP error under this model. So the high-level idea of our work is that we consider a clustering problem, which is a discrete problem, but we study a continuous optimization-based algorithm for this problem, and our result shows that somehow the error of the continuous optimization-based algorithm can be controlled in terms of the error of this discrete optimization-based formulation. So, thanks.
Okay, we have time for questions.
Bigger than K, yes. I don't think it's information theoretically necessary. There might be other algorithms that works under this SNR ratio, but my guess is that it's necessary for this SDP relaxation approach. But we don't have a proof for that.
We had one more quick question.
So the question is why we consider the L1 metric. Somehow we believe that this is the natural and appropriate metric for this problem because our goal is to recover this clustering matrix that is 0, 1 valued. So the L1 metric somehow, in some sense, counts the number of entries that are wrong. And in that sense, we believe it's the appropriate metric for this kind of problem. But of course, if you're interested in the L2 metric, you can always convert them. But we believe the L1 metric gives us the tightest result.
Okay, great. Let's thank the speaker again. So the next